In part 2 of this video, we're going to consider the connections between natural log function and also trig functions. So first we'll integrate the tangent of x. This one's tricky because I know what to do if I saw secant squared, and I know what to do if it was secant tangent, but tangent itself is different. So I'm not sure what to do, but I do know that I could rewrite this as the sine of x over the cosine of x and maybe consider u substitution. Now the first choice that most people would make for u substitution is to say that u equals the sine of x. And they're thinking, oh yeah, because then I'll have all my pieces. The derivative of sine is cosine of x dx. But the problem with this is that cosine's in the denominator. So that's the same as cosine of x to the -1 power. And so the relationship isn't what it appears to be if you're not paying attention. So sometimes u substitution doesn't work because your choice of u just doesn't work out. So we're going to switch it around and say that u equals the cosine of x, which means that du equals negative sine x dx, or more importantly, negative du equals sine x dx. Now I can make my substitutions and use u substitution. This will become negative times the integral of 1 over u du. And that connects to what we've been doing because 1 over u integrates to the natural log of the absolute value of u plus c, and since u equals the cosine of x, we can reach our conclusion. So we employed some trig identities and just paid some attention to things. Next example, let's deal with the cotangent of 3x dx. Again, I'm not sure offhand what's going to happen with the cotangent of 3x dx, but I do know that I can rewrite this as the cosine of 3x over the sine of 3x dx, and that if u equals the sine of 3x, that means that du equals 3 cosine 3x dx, or dividing both sides by 3, a third of du equals cosine of 3x dx. So now by u substitution, this becomes 1/3 times the integral of 1 over u du. And we can see what's going to happen from this. This will be 1/3 times the natural log of the absolute value of u plus c, and since u had the value of the sine of 3x, we've got our conclusion. A few more. Hopefully we'll have enough room here. Let's consider the integral of the cosine of x over 2 plus sine x dx. Again, u substitution seems to be a way to go. I'm going to substitute for the denominator 2 plus sine x in this case, which means that du equals the cosine of x dx. And I'm real happy with what I'm seeing because now I can integrate this. This will be the integral of 1 over u du, which becomes the natural log of the absolute value of u plus c, and since u has that value of 2 plus sine of x, my final answer is the natural log of the absolute value of 2 plus the sine of x plus c. A few examples left. Let's consider the integral of 1 over cosine squared x of tangent x dx. And I'm not really sure what to do, but one thing I do recognize relationally is that 1 over cosine squared is the same as secant squared. And I'm going to rewrite this because now I can see how u substitution will benefit me, because I know the derivative of tangent x is secant squared x. So if I let u equal tangent x, then this means that du equals secant squared x dx. So So by u substitution, this will become the integral of 1 over u du, which is the natural log of the absolute value of u plus c, and u had the value of the tangent of x. So again, being real fluent and fluid with my trig identities helps out a lot here. Let's do some definite integrals. So we've got the integral from 0 to 4 of 4 over 2x plus 1 dx. I'm going to just pound this through with the chain rule. This would have come from 4 times the natural log of the absolute value of 2x plus 1. And I'll need to ultimately evaluate this from 0 to 4. But by the chain rule, I would have taken the derivative of 2x and had a 2 out here. So I'm going to counteract that by dividing this value by 2. Right, so I'm just making sure that I'm undoing the chain rule the whole way. Now when I evaluate this at 4, I'll have 2 times the natural log of 5 minus, when I substitute in 0, I'll have 2 times the natural log of 1, but the natural log of 1 is 0, so my final answer for this is 2 times the natural log of 5. And since 5 is positive, I can just drop the absolute value bars. There's no need for it, although it wouldn't be wrong to have it there. Two more definite integrals to consider. Let's look at the integral from e to e squared. I'm not going to panic because I know that those are numbers that are related to the natural log of 1 over x times the natural log of x dx. In this case, I'm going to use u substitution. If u equals the natural log of x, then du equals 1 over x dx. So for u substitution, this is simply going to change to 1 over u du. I'm going to change my limits of integration. If x is e squared, then the natural log of e squared is equal to just 2. So that's my upper limit of integration. If x has the value of e, then the natural log of e is just 1. So now I'm evaluating this whole thing from 1 to 2. The integral of 1 over u is the natural log of the absolute value of u, and I'll evaluate that from 1 to 2. This will be the natural log of 2 minus the natural log of 1, but the natural log of 1 is 0, so this simplifies down to the natural log of 2. Last problem is a definite integral that is involving some trigonometry. So we're looking at the integral from 0 to pi halves of sine x over 1 plus cosine x, and this integral looks suspiciously like number 11, so I'm expecting some similarities here, but I'll do u substitution to keep everything straight. If u equals 1 plus cosine x, and this means that du equals negative sine x dx. So first I'll change my integrand. In this case that will be negative 1 over u du. Now I'll change my limits of integration. If x has the value of pi halves, then 1 plus cosine of pi halves is my upper limit of integration. The cosine of pi halves is 0, so my upper limit would be 1. When x has the value of 0, 1 plus the cosine of 0 is my lower limit of integration. The cosine of 0 is 1, so this will be 2. Now I could integrate it this way, but one property that I can use is, since I'm going backwards from currently from integrating, my lower limit is 2 and my upper limit is 1, and that's backwards. If I reverse this, that changes the sign of my integral. So this is the same thing as the integral from 1 to 2 of 1 over u du. Integrating that, we end up with the natural log of the absolute value of u from 1 to 2, which is the natural log of 2 minus the natural log of 1, but the natural log of 1 is 0, and my answer is again the natural log of 2. So this should set you free with regards to attacking a lot of different problems involving integration and relationships to the natural log function.